Okay, so yeah, since we don't have enough time, I will just use my notes. So I won't. So can you see the screen? Yeah, can you see the screen?
Yes.
Okay. Thanks. Yeah. Okay. Yes. Yes. Yeah. Thanks. Okay. Okay. Let's just start. Okay. So so let's talk about martingales. So it's basically some function of Brownian motions, as you see. So in this lecture, so all the martingales, continuous in time martingales, so we will show the Brownian motion is a martingale, right? So they have some filtration Ft, so we will mention, and also some composition of this Brownian motions, right? A function which depends on time also depends on the x variable. So this might be a martingales as well. So of course, when we say something is a martingale, right? The basic property is just this. So I will add one more page. Okay. That's bad. Huh, yeah, I'll just write and okay. Okay, when I say martingale, what does it mean, right? So in discrete times, this means xn, right? If xn is a martingale, right? So of course, xn is a sequence of random variables, right? Or you can say stochastic process, which generating the filtration, right? It can be generated by the first n terms. So then xn is a martingale, right? If you take n fm, you take the conditional expectation, we get xm, right? So n is bigger than m, right? So this is called martingale, right? Martingale basically says, right, conditional expectation doesn't change, right? This implies the expected value does not change over time. This is the same, right? This is exactly the same for entire martingales, right? So here, let's say xt, and we also have increasing filtration ft. So increasing filtration, right? This is increasing. But usually we assume this ft has a property, right? So ft, we assume ft is right continuous. So right continuous. So this is increasing. Right continuous means, right, if you take all the intersection for t bigger than s, right, you take the intersection for all for this filtration, so we just get fs, right? This is right continuous. Basically, you can approximate fs from above, right? From above. So this is called right continuous. So under all those assumptions, right? So martingale basically, right, is again, right, means this. We get st fs, so take conditional expectation. So we just get xs for all t than s, right? So we need other conditions as well, but this is the crucial one, right? So conditional expectation agrees with the previous time random variables. Right? This is almost everything, right? But we need some integrability condition, right? This is integrable random variable, right? To make those notation meaningful. Okay. So let's say the first result, right? The first result, we have the same counterpart for discrete, I believe is theory 4.1. So basically says, right, if we have a stopping time, then we have ext equals to ex0. Okay, you have the same thing. You have the same thing. Yeah, but we need, but for simplicity, we can extend later. But for simplicity, we assume so t is bounded stopping time. So bounded is actually means this, right? There exist n, right? There exist integers such as this equals 0. This is right. So almost surely, right? T is bounded by an integer n, by integer n. Okay, for a bounded stopping time, we have this. A priori, right, by Martingale property, we know the following is true, right? Ex0 right, equals to ext, right? Because this is Martingale, right? So this should be true for any e bigger than 0. And this also equals to any xs, right? This theory tells us, right, if you change the fixed time t to a stopping time, this should be also true. I mean, so now we don't feel this is then surprising because we already see the discrete analog of this theory. But if you first time see this theory, actually is kind of surprising, right? Because so this xt, so this xt is actually, right, you stop at different time, right? And you take a slice in those. So for instance, right, you have a stochastic process, right? Something like this. These different trajectories, right? So you may stop here, right? You may stop here, right? So, but if you take a conditional expectation, let's say on this slice, right? So you get the exactly the same, right, as the initial data, right? But since we already have know the discrete result is true, right? This is not that surprising. Okay, so I will just sketch the proof. Actually, it's a complete proof, but we won't do like full details. I will just tells you, right, how this can be proved. Okay, so we use the result for discrete martingales. Then we pass to the limit. Right? Okay, so let's assume this stopping time t is bounded by n minus 1. Okay. So why we choose like this, you will see that later, but this is not really important. So let's assume this stopping time is less than or equal to n minus 1. And we define a sequence. This is Tm. So this Tm define a sequence of stopping time. So this definition is exactly exactly what we did before we stated the strong Markov property. So you can check this Tm, right? You can check this Tm satisfy the following property. Satisfy the following property. So if t is between n to n plus 1, but we divide by 2m, okay? So then t just equals to the bigger one, equals to the bigger one. So actually Tm is a stopping time which uniformly approximates t from above. So Tm, right? So it's always bigger than or equals to t, right? And Tm is decreasing. So Tm is decreasing, okay? And the distance in Tm and minus t, right, is less than 2m. Right? So by this observation, okay. So we just take those discrete times, right? So those discrete, we just take all those discrete times, right? Let's fix m first. Fix m first and take all the discrete time m, right? The discrete time in this form, right? This is all the discrete time. It's like in the time interval, take the discrete time slice, okay? And also we take the discrete time, discrete filtration, right? So this filtration is just generating by those discrete times, okay? So we want to use this as a time for discrete martingales, right? So this is easy to get, right? We just multiply 2m, right? So we get Sm. So now Sm actually equals to 1, 2, 3, etc., right? So this Sm is a stopping time, and Sm is a discrete times, right? It's a discrete stopping time. We can show, right? So with YKM, right, is just a get by taking the discrete slice of the continuous martingale. So of course, those YKM is a discrete martingale, right? So we just take a discrete time slice, right, here, right? Just take discrete time slice. So previous XT is a martingale, right? So of course, this YKM is, right? YKM is, okay. So we can use the property, right? We can use the property of the discrete martingale, right? Discrete in time martingale. So what's that, right? It's just the following. This is not a well-known fact, right? Not well-known, but we really put this in exercise, in homework, I guess. So what's the theory says, right? So I just copy here. I just copy here. Right? This is what we use. It's xi is 4.4.2. So if xn is a submartingale and m is less than n, right? So then we have the following things, right? But here, right? But here actually Sm. Here actually so, but here so we just take n equals to Sm, okay, and we take m. Oh, sorry, we take m. The smaller one is Sm, and we take the bigger one is fixed. The stopping time, right? Stopping time, fixed stopping time, and we apply the theory. The theory here. The theory says, right, if X is a submartingale, then we have this estimate, we have this control, and this control becomes equality, right, if X is a martingale, right? So that's why we get here. That's why we get here. We apply the result here for martingales. So we get the equality. We get the equality, right? We get equality for martingales. We get equality, and by our choice, our definition of y, right? So this term is exactly xn, right? So this is the filtration FM, right? So we get the inequality, right? We get this equality, right? So other two equality just by definition, right, is trivial. That's the definition. Okay. So then we just pass to limit, right? We send m goes to infinity, right? We send m goes to infinity, right? So we send m goes to infinity since Tm uniformly approximate x, right? The stopping time. We know the Tm is a sequence approximate t, right? And also this is a filtration, the filtration. And by the theory we stated in last lecture, this approximate ft, and ft is the smallest one. Right? Ft is the smallest one. So here we use another theory, talk about in the backwards martingale. Right? So this is another theory I stated here. What this theory says, right? So given a random variable y, right? So let's assume this is a variable, this is integrable. So if we have a filtration which is decreasing, you have a decreasing filtration, then automatically we have the conditional expectation converge both almost surely and in L1. Right? So that's why we get the convergence of the right-hand side here, right? So this we have convergence, right, almost surely, and this we have convergence almost surely, right? So we get the convergence in the end, right? So that's why in the end we get this result, okay? We get this result. So almost surely. So now we just taking expectation, right? If you're taking expectation of this term, right? We just get this, right? By martingale property, right? So these two are equal. So then we get the result, right? Get the result. Okay, so let's go back to see, right? The final result is this equals to this, right? The conditional expectation of the martingale with, right? We use the time and stopping time t, right? Is equals to ex0. But on the condition t is less than almost surely, t is bounded. T is bounded. Okay, so let's just give you let you look at the main result again, right? So this result says, right, so as long as xt is a martingale, but the xt is continuous as well, so you can approximate xt from above, right, from a larger time. And this xt adapt to a right continuous filtration ft, right? Right continuous filtration ft. So then if t is a bounded stopping time, then we have this the conditional expectation agree with each other. So this is a very useful result, right? As we did for discrete martingales, right? So so there are a lot of things, right? Let's say we want to compute the exit time, right? Distribution of exit time, the hitting time, right? And something related to the maximal or minimal of a trajectory. Then you need the presence of the stopping time, right? And we want to use this equality to get some quantitative result, right? So this result is very useful. Okay, you can just think this as a continuous version of the theory 4.4.1, right? So in section 4.4.1, we're talking about the Dubs inequality, right? And the LP maximal inequality, something like that, right? So this is the first result in that section. Okay, so as a very easy application, right? Because we are talking about Brownian motion, we want to say the Brownian motion is really a martingale, right? I mean, this everybody knows, right? So this is not like a super surprising. But we need to be clear about the setting, right? So in last lecture, I said a little bit, but maybe not in very detailed way. So it's maybe a little bit rushed. But now let's state this again, right? You don't need to know, right, the full details, but at least you should know, right? Later, when you're talking about Brownian motion, is a martingale. What does this mean, right? And this page basically tells you all you need to know. Okay. So BT, Brownian motion, right? Usually, right, is a Brownian motion. So with respect, right? So of course, BT is right continuous, right? BT actually is a Holder continuous. Is Holder continuous, but gamma is less than 1/2. Okay. So what's the FT here? What equation here, FT, right? So if you still remember, right, in last lecture and also in the lecture before, maybe, so we define Fs, right? So this is called Fs0. So it's all the history, right? It's all the history up to time S, right? So this is F0, but in the discussion of Blumenthal 0-1 law and other, right, the Markov property, strong Markov property. So we use this Fs plus actually, right? So this Fs plus actually is the intersection of all the Fs0 for S is bigger than T, right? So all the of Ft0 for T is bigger than S, right? So of course this is bigger than Fs0. This is bigger than Fs0. But from our previous discussion in last lecture, so these two sigma field, right, or you can say these two filtrations agrees with each other almost surely, right? So when you say almost surely, right, so they are equal to each other up to a null set. So null set means, right, in probability, right, the probability charge this set zero mass, right? So it has probability 0, right? So up to probability 0 says, right, so fs plus and fs0 are the same. Okay, so usually, right, later, right, we use this convention, right? So how to do this fs? So we put first, right, we put all the null set, right? We add all the null set there, right? So if D is has probability 0, then all the subset in D, right, even is not a variable, right, we put there. So then A is a null set, or we put all the null set there, and then this fs plus and take the union with the null set, right? These two generating a new sigma field. This sigma field is complete, right? We call this fsx. Okay. Then we don't want the sigma field depends on the initial state x, right? So we take the initial of all the initial state x, right? So in the end, we get fsx. So sorry, we get fs. So later, when we're talking about filtration for Brownian motion, right? So we just means the above construction, right? So ft is or fs is constructed by this line, Okay. So it basically, it put all the now there, which depends on initial state, right? Then we take the intersection. Okay, this fs is actually, right, it's really a sigma field, right? You can check this is really a sigma field. And also this is right continuous. So this is right continuous. So fs is right continuous simply by, so this simply is by this fs plus, right? So is right continuous. Is right continuous. Okay, so I will just leave the checking for you, right? I write something here, right? It's easy to check in. But later when we're talking about Brownian motion, right? The sigma field we are using is just constructed by this this line, right? This discussion. Okay. So to prove Brownian motion is a martingale, right? It's too easy, right? Because we have independence, right? When we construct Brownian motion, right, it's simply by Markov property, right? So when we construct Brownian motion, right, so we already assume, right? So T, right, this is T1, right, this is T2, right? So these two are independent, right? Increment on these two on disjoint intervals are independent, right? It's basically Markov property. So we can show Brownian motion martingales, right? But we need to say this, right? We need to say this clearly, right? So how to write this, right? Just one line. So is, yeah, maybe you see this line is better. This line is better, right? So we choose T, we choose T is bigger than S, we choose T bigger than S, and we want to show this equals to this, right? This equals to this. This really equals to that, then, but we want to say in the end it equals to BS, right? So this is the martingale, this is martingale, right? So we need to check this, right? So how to check that, right? So you can say, right, we can write the first one, right, equals to this, right? So if you shift a little bit, right, if you shift a little bit, right, so here you need to take the difference as well, right? So this is equal. So then using the martingale property, using the Markov property, right? So you take conditional expectations, and everything matters is the value and BS, right? So this is what we get, right? This is what we get. Then, so we're starting from BS and we move according to normal distribution with variance T minus S. So then the mean should really be BS, right? So if you're starting from Y and so the movement is according to normal distribution, of course, right? The mean is just Y, right? The checking is very simple, right? We just using Markov property and the normal distribution, right? We're starting from y, the mean is y as well, right? So, so of course, right? So Markov Brownian motion is martingale. Right? So this is a basic fact. The checking is as easy as possible. Right? Okay. So as a corollary, right? So here I said, right, you can compare to theory 4. So this is for random work. So symmetric and asymmetric random work on 1D. Okay. So symmetric or asymmetric random work on 1D. So we have exactly the same result for random work, right? So result is very easy. So what does this say, right? So the sentiment is exactly the same for random works, right? But I still want to say this, right? So it says, right, if you're starting from X, right, you're starting from X, this is a heating time, right? So TA is a heating time to A. So TB is a heating time to B, right? So we want to find the probability, right? TA is less than TB, right? So TA less than TB means starting from X, the Brownian motion, right? So heating the Brownian motion, heating A first. The Brownian motion heating A first. So then the probability is equals to this over this, right? So the probability is proportional to the length, right? B minus over the whole length, right? This makes sense, right? So if A is more close to X, right? So it is more easy to exit this interval from A, right? So then this makes perfect sense, right? Because the Brownian motion is symmetric, right? Symmetric. Brownian motion is a scaling limit of random walk, right? So we expect this theory is true since Brownian motion is just a continuous version of random walk. Okay, the proof is easy, but I want to say this and skip all other proof, right? Because all other proof basically follows the same strategy here, right? So I will just go through this proof, make some comments, but I will skip other proof similar to this later. Right? Okay, so how do we prove this, right? The idea is exactly the same as in random works. Okay, so let's write a new stopping time, right? T is a stopping time because this is a minimum of two stopping time, TA and TB. So T is a stopping time, and we know T is finite almost surely. So why this is true, right? Why T is finite, right? So by the following theory, right? This theory we proved actually in details in last lecture. So if BT is a 1D Brownian motion starting from 0, then almost surely, right? So it visit infinite and it visit minus infinite, infinite often. And even you scales like this, right? Even scales like this is true. Okay. We have a more precise characterization of Brownian motion. So it's called iterated logarithmic law. But so this theory basically tells us the following, right? So and it makes sense, right? So let's say this is a square root, right? Square root t, right? Square root t. So this is also minus square root t. Right? So we know BT is a normal distribution, right, with mean 0 and the variance t, right? So and time, so let's say this is and time t. So and time t actually Brownian motion is like a Gaussian, right, distribution with center 0, and this is a one variance, right, one variance. So most likely, right, Brownian motion is like going something, right? But it cannot go very far from square root of t, right? So because the square root of t is the standard deviation of bt, right? So it visits 0, right? It can visit 0 infinite often and go up to square root of t and go down up to minus square root of t, right? but they cannot be too far from square root t, right? Okay, yeah, okay. I mean, I said not too far, right? In like probabilities, right? But if you take the lim soup, right? Of course, you can go to positive infinite, right? So this makes sense, right? So by this theory, we see, right, if you take t goes to infinity, actually, right, so definitely, right, bt can go out of this interval, right? Of course, you can go out of this interval. So almost surely t is finite, right? Because for typical trajectory, you can always go to positive infinity and negative infinity, right? So definitely you can go out of AB, right? So if we want to use the previous result, we need to take a bounded truncation, right? So t is a bounded fixed number, right? So t with t which t, small t, is a bounded stopping time. So we can use the previous result, right? The result we showed in this lecture. So then we can use that, right? So then, right, so this is the Brownian motion and stopping time, right? This is the initial state, or starting from x, right? So this should be x, okay? And we know, right, since this is, we stop at time t, right? T is the exit time. So this Brownian motion is bounded, right? Is bounded by A and B, right? By A and B, actually. So now, right, we can use in the bounded convergence theory, where we send time goes to infinity. With t, since t is finite, almost surely, right? So if you send t goes to infinity, so this just goes to t, right? So by bounded convergence theory, we can pass to the limit, right? So we get this. We get this. So we can express this formula, right, using the probability TA is less than TB and probability TA is bigger than TB, right? So TA cannot be TB, right? Because you cannot exit A and B at the same time. Right? So rearranging these terms, we can prove the theory, right? So it's exactly the same we did like before, but we need this result, right? We need this result. Right? Also, you can compute this explicitly, right? Okay. Okay, so this says, right, this says we can compute the probability exiting from A and B, right? If you're starting from A, we can compute the probability, right? So you exit A first or you exit B first, right? Okay, the following theory, just want to skip that, but so what it says, right? This says if you take square or BT square, and you minus t, and then you get a martingale answer. Okay. So the proof is easier, but I want to emphasize, right? This is exactly the following, right? The discrete analog is this, right? You have a random walk. So if we have random walk Sn, which is the sum of n IID, right? Xi, I, D, right? So then we can show, right, Sn square, right? So let's say Xi has mean zero, and standard deviation sigma, variance is sigma square. So then Sn square minus n sigma square is a martingale. Right? So exactly what the discrete version is, right? Okay, the checking is very easy, right? So I'm very sure you can check that, right? Just in two sentences. Okay, so the following is also very easy, right? So we can check him, we can compute explicitly the expectation, right? Of you, if you accept the Brownian motion, you're starting from zero, and we want to compute the exit time of this time interval, B. And we can compute the expectation of E0t, E0t of the exit time t. And later we can even compute the expectation of the t square. Right. So maybe more, right? We can take computing all the moments, right? We can compute all the moments just by constructing a sequence of martingales. Right? So here we can compute this because this bt square minus t So this is a martingale. So we can do this because ET squared minus is a martingale. If you ignore everything, just using this is a martingale, and also assume T is nice, right? T is nice. Otherwise, you can just pass to limit using the pass to limit theory, right? Continue integration to limit theory. Okay, anyway, so let's assume this is true, right? Because BT squared minus T is a martingale. So we can compute E0T. We can compute E0T just by compute this. So which is minus AB. Yeah, so it's an easy exercise. So I will just say a few words and skip that. So if you have questions, you can ask, right? But since there are discrete analog before, right? So we did this before. There's no new part, right? So I will just skip this. Okay, but the following one is very useful. So I will discuss more. So it's a very important observation. So it's motivation to study like Ito calculus, right? Ito formula. So it's a good motivation. Okay. But here, right, since we know nothing about by Ito's formula, so we just checking this directly. So we claim this I mean, of course, it's Markov process. So we claim this stochastic process is a martingale. Right, this stochastic process is a martingale. Why, right? So by checking, right? So I cannot say, but actually these two coefficient, right? These two coefficient you cannot change, right? So if you fix the coefficient theta before BT, right? Then the coefficient before T is just a minus sigma square over T. And this is this has meaning, right? So this is not just like arbitrary martingale, let this ST. So this xt, right? So we can check, right? You will see in a minute. If you take the dst over st, right? You take dst, right? So it's the total differentiation. But since here we have Brownian motion, we are not very clear what is the total differentiation means. But anyway, so I just write this. So actually, this is just a dbt. So what does this mean, right? So this is a relative change of ST, right? So you can think ST price of is some stock, right, in stock market. So this is a relative change, right? This is a price or a relative change of the price. And this model basically says, right, the relative change of the price is Brownian motion, right? Theta is just a parameter, okay? And then, right, if you model like this, right, so then you can solve ST, right? Then ST is just given by this form, okay? And this basically says the price, right? This baby model for stock market price is a martingale, okay? So we can check this directly. It's not as straightforward as before, but not hard since BS is a normal distribution, but we can compute this, right? Okay, let's just compute that. Okay, to show the result, right? We want to show, right? So this is the ST. Right? If you project to FS, we hope to get this equals to ST, right? We hope to get this is ST, right? So then we just checking, right? Just checking those terms, right? This factor can be put out, right? So we can just check this part. We can just check this part. Okay, how to do that, right? The idea is simple, right? As in the homework, right? Just break T to the BS part, right? And the increment part. Right? So, right, so the first part, this part is FS measurable. So we can put this out, We can put this out. So then we're just taking the conditional expectation of the increment, right? So with respect to fs, okay? So we can just compute this hastily, right? These two, right? This increment and fs are independent, right? So here the conditional expectation actually agrees with the expectation, right? This is just equal to bt minus bs, and bt minus bs has a normal distribution, right, with center 0 and a standard deviation square root t minus s, right? So we can compute this, right? We can compute this. Here, the following is just computation, right? You can do that by yourself, right? So this is e2 theta x, right? So this is the PDF, it's the PDF. And we can just compute that, right? How to compute that? We just complete the square. So we complete the square, right? We can say this is the term we have, and this is the term we have. So we complete the square, right? There's one more term here, so we take it back, right? So there's a minus term here, right? So we multiply back, right? So in the end, we just get the explicit value of this integral. So if you compare, right? If you compare, right? If you multiply, right? The factor e2 minus theta square, you multiply this factor back, you just get this is a martingale. You just get this is a martingale. Okay, this is the conclusion. ST, SD here is a martingale. This is a martingale. Okay, so as I said, right? So if you take the relative change, right? You take the relative change, you just get this. How to show that, right? So we haven't learned anything about Ito formula, but we can assume we know that, right? So this is a good motivation. So let's assume we know Ito formula. Okay. So this is f, right? This is function f. This is function f, right? Depends on time and also depends on x, right? So we write this as function. Right? This is just a Euler smooth function, right? F is smooth. F is smooth, but we don't need it smooth, right? We only need is second order differentiable in x and first order differentiable in t. Right? But here actually is smooth, right? It's smooth both in x and t. Okay, so let's assume we know the Ito formula. Let's assume we know Ito formula. So what is Ito formula, right? So in this specific setting, right, you take the differentiation of f, right? So what was the formula? Is it okay? We first take differentiation. We take derivative in t, right? dt. We take derivative in x, right? Then dt dbt. Okay, so if this is the Euler differentiation, right, in calculus, we are done, right, in the first two terms. But this is not a Euler differentiation, right? So we have one more term. So it's dbt squared, right? So it's like a Taylor expansion to second order. Taylor expansion to second order, and we keep all the terms has non-zero contributions, right? So this term has non-zero contribution as well. So later we will see, right, dbt square is just a dt. So dbt square is just a dt. So this is kind of in the spirit of theory, not theory, is a homework problem. Homework problem. Let's see, it's 7.1.6, I guess. Yeah, I guess it's 6. This is a last homework problem. But intuitively, we can think, right, dbt square is like dt, right? So this is an old Ito's formula. Ito's formula. Okay, so if you're using this specific setting, right? So then this is partial tf plus this second order term, dt, right? Plus this term plus dbt, right? And we can show, right, these terms vanish, this vanish, really vanish. So why, right? So it's very easy to check, right? Partial TF here, right? So equals to minus 2 sigma square F, right? So partial Fx, right, equals to, right? We just take 1 theta out, right? So F. So again, partial x square F, right? Second derivative, it just equals sigma square F, right? So this term equals to 0, right? So the drift term vanish, right? So if we apply Ito's formula, the drift term vanish. So in the end, we just get this term, right? So that's what we get, right? That's what we get, right? So that's so then we get df tbt, so equals to theta f, right? tbt dbt. I mean, now, right, this is just a formal writing, right? Later we will specify this, right? So then, right, if you divide by s, right, so df over f, right, so equals to theta dbt, which is exactly this formula, right, this formula, right? So ds over st, right, is the relative change, right? It's relative change, right? It's not just a change itself, right? If you change is so if your original price is $100, right? So the ds is like $10, right? And the relative change is 10%, right? So the relative change matters in most of the time, right? It's not the the absolute value, right? The relative value, right? Relative change is a Brownian motion. Okay. Okay. So this tells us, right, this is a model, right? So this is a martingale, right? This is a martingale. There. Okay. So there's one more example, right? Using the property, right? This is a martingale, but I will skip this. But I will skip this. But I will skip this. So ST is a martingale. So ST is a martingale. Using this observation, so we can compute the Laplace transform of of TX, right? TA. So TA is just the heating time of the Brownian motion, right? And the location A. So in last lecture, right, we know how to compute the distribution of TA. Right, we know how to compute the distribution of TA, right? So now, right, this by martingale, by ST is a martingale, it's more specific, it's more easy to compute the Laplace transform of TA, right, the heating time. But I won't talk about that. It's relatively easy, right? So so you can find the proof here. So now let's talk about another thing, right? It's more important, right? So, and it's maybe not more important, but it's more relevant, right? So it's like relation to heat equation. Right? It's a relation to heat equation. As I told you, so if you have a Brownian motion, Bt, t bigger than 0, it's a Brownian motion. So actually, right, so if we write Pt Pxy, right, Ptxy is the law of the Brownian motion is starting from x, b0, bt. So there's a law of Brownian motion. Law means the distribution of Brownian motion starting from x. So law, right, also maybe it's better to just call this PDF. This is a PDF of Brownian motion starting from x and time t. So this is a PDF, right, probability density function. So this is a well-known fact. This partial pt x, y, right, fixed x, right, we're starting from x. So this is solves heat equation. Solves heat equation ptxy. But here is take derivative with respect to y. So Brownian motion is just heat diffusion, right? It's not that magical, right? So we just write the law, the PDF of Brownian motion, so you can obtain a heat equation for its density function. Right? Okay, probably if you don't check this before, right? I suggest you to just do the computation, right? So this is a transition function, right, or the PDF of normal distribution with center 0 and variance t, right? So we write this formula. So you can check, actually PT is a fundamental solution of the heat equation. So when I say fundamental solution, it means, right, you're starting from Dirac, right? You can solve the heat equation, right? This is the heat equation. So heat equation probably is the, so one of the first equations ever written, right? One of the first PDEs ever written in the history. So we can solve everything, right, starting from delta x or Dirac. So then you can solve the heat equation. You can check this, right? You can check this PTXY really solves, right? You can check the density function really solves the heat equation. Right? It's an easy check, but I suggest you to do that. So you just check here. Just check here, right? So this is the check-in, right? So you can check, right? So this PT, right? Just a fundamental solution of the heat equation. Right? So here we want to show a theory. It's a general theory. It says, right, if we have a smooth function, so let's assume, right, this is not necessarily should be a polynomial. So let's assume U is continuous, right? Is xt. So when I write this this way, it means, right? So if you take a derivative in x, right, it's like partial derivative in x, right? So this continues, right? And also we can take a second order derivative, right? This is all continuous, right? Continuous. Take the first order derivative in t, right? So this is continuous. This is continuous. So, and also we need a u decay fast enough. Okay, u and the derivative of u decays fast enough. So with this assumption, right, or in the textbook, right, it assumes, right, u is a polynomial. So I says, so it decays fast enough, right? But sometimes it's not decay, right? So you can grow, right? But you cannot grow too fast, right? Or we can say, right, so u does not grow too fast. Does not grow fast. And this u solves this equation, right? So you see, right, this kind of the duality of the heat equation, right? Right, it's not a heat equation, right? Because this is really plus, right? U does not solve the heat equation, but it's kind of electric heat equation, right? It's kind of due of heat equation, but I don't say this is exactly due like in analysis because it's not. Right? But anyway, as you satisfy some regularity and solve this equation, let's call this equation star. So then U is a martingale. Right? U is martingale. So I can tell you, right? So this theory, this series, right? This theory captures, right, the previous discussion, right? It captures this discussion, right? It captures this, right? And also BT, and also this one, right? And also this one. So why, right? So let me show you, right? Let me show you just a bit, right? So as an example, right? Let's say as an example, so we can take UTX, right? We can take UTX as exponential, right? Theta x minus t. So you can check, right? This equation holds, right? But you can see, right? This is not a polynomial, right? Not a polynomial. Right? This is not a polynomial, right? So this theory, you don't need it to be polynomial. Also, you can check ut equals to x squared, right? X squared minus t. You can also choose a lot of others. Just to give you one more example. So you can also choose uxt equals x cubed minus 3tx, right? So you can keep doing this, right? You can write the third, you can write a polynomial, right, with x in degree 4, right? So and etc. You can keep doing this, right? You can if one is give you polynomial, right? And this star, right? This equation is really linear equation, right? You can do linear combination, right? So in the end, right? So this is a general function class, right? So in this general function class, right, so as long as you solve this with certain regularity, so we can, this is a martingale. So once we have this martingale, right, it's very good, right, because we can compute some values, right, explicitly, right. So this is why martingale is important, right. So because martingales we can write, and at least we can write, take expectation, it equals to the initial time expectation, and we can choose different slides, right, using stopping time, right. So martingale is a very good notion, right? So it's a key notion in probability. So sometimes, right, if you have a martingale, right, if you can show process is a martingale, right, it's very good. You cannot show it's a martingale. We also want to relate it to be related to another martingale, right? Maybe change a variable or something, some other techniques, right? Okay, so that's why we should really talk about this. Okay, so this is a general theory, and the proof, I won't give you the full proof, but I want to emphasize why this is true, right? Why this is true. It's basically just the integration by parts, right? If we forget other technical details, so basically this is just this page, right? So all the basic idea is coming from here, this page. Okay. If you have questions, please ask. Yeah, maybe these few lectures are fast, so you probably, if you didn't prepare first, maybe not follow closely. Yeah. Okay. Okay. Good. Okay. So as I said, basically integration by parts. Okay. So let's so to make this martingale, right, a priori, right, not a priori, prerequisite is this to be a constant, right? So I mean, if UTBT is a martingale, then right, you take the expectation, right? So this should be the same, right? This should be the same, right? This should be the same, right? So if we taking the time derivative along the trajectory, right? So this should be 0, right? As I said, this is a prerequisite, right? So you need to check this is true, right? So as long as this is true, right, you can use the Markov property to show, right, this is really a martingale, right? But the really important part is here, right? So why we impose, right? Why impose this condition, right? And this computation tells you why we impose this condition, right? I mean, this is a 1D case, right? In high dimensional, right, is the Laplacian operator, right? Laplacian operator. So we just do the commutation, right? We write the time derivative, right? So then this is u, right? Using the probability density function, right? Then we take in derivative, right? Take the derivative inside the integral, right? Interchange, right? The order of integral and derivative, right? So now we're using the chain rule, right? So here is just a chain rule, right? We take derivative with the first one, right? Then we take derivative with the second one. So so then for the second term, right, we're using the heat equation. So here we're using heat equation. So we're using heat equation, right? So we get 1 over partial y squared. Then, so from this term to this term, we're using integration by parts. So to make integration by parts, right? So here is integration by parts. To make integration by parts makes sense, right? So we need some decay property, right? So that's why we assume u should be polynomial, right? It does not grow too fast in infinite, right? But let's assume everything is okay, right? It's fine. So we can integration by parts. So this second order derivative is exchanged to u, right? It's exchanged to u, right? So that's why we get pt here. And the second order derivative is passed to u, right? And we know, right, we collecting terms, right? So then we get this equation, right? So u solves this equation. Right? U solves this equation, right? So we get 0, right? So this term, so these two terms adds to 0, right? So this adds to 0, so that's why we get 0, right? And so actually this is a crucial computation, right? So later it's just checking, right? Using Markov property. So I will leave that as exercise. Okay, I will leave that as exercise, right? So there are other discussions as well, right? So you see, right? As long as the integration by parts makes sense, we know this u t bt is a martingale, right? Is a martingale. So as long as partial tu plus 1/2 partial x squared u equals to 0, right? Equals to 0. So this equals to 0, okay? So using this observation, right? Using this observation, so actually using this, I guess. So you can check this v, right? This v solves. You can check this v solves partial tv, right? Plus 1/2 partial x squared u equals to 0. And we can using this to compute, right, the expectation, right, of t squared, right, t squared. As I said, well, you can keep doing this and you can show, right, you can probably compute each t cubed, right, t false, right, you can keep computing like all the moments of this t, right. I mean, right, we already know all the Laplace transform of t, right, so that this makes sense. So we skip those discussion. If you have questions, I can answer, but all those are standard. I will just stop here, right, and wait for a bit. Then I will go to next section. So this is all the discussion for martingales. Okay. Any questions? So any questions? Okay. So if you have no question, right, just let me write a few, right? What we did, right? What we did. So BT, right? So what we did, right? So what you should know, right? So BT is a martingale, right? And so basically we are building up a lot of martingales starting from BT. It's a martingale. So the filtration is just FT, right? So we are building up, right? So I mean, firstly, right, we just checking this, right, by our intuition, right? So this is a martingale. This is a martingale. This is a martingale. And also, right, so st, right, equals to exponential theta Brownian motion minus 1/2 theta square t, right? So this is a Brownian motion. This is Martingale as well, right? Martingale. So Martingale as well. So last series says, right, so if you have u, right, this t, this bt. So this is a Martingale. So if and only if, so u solves partial t plus 1/2 partial x squared u equals to 0. And u is smooth enough and does not grow too fast and infinite, right? So as long as you have this property where we have a general class of u, right, of martingales, right? So I can tell you, right? I can tell you, in general, right? What is a martingale, right? In general, what is martingale? In general, if xt is a martingale, if xt is a martingale, so then you take the differentiation. You take the differentiation. So then this should be equals to theta t xt bt. So it's 0, right? So there are no drift term, right? No term. Okay, in general, right? So let's bank up one step, right? Let's go back. Let's read. Let's. So let's write a general family of diffusion, right? You probably see that before, right? You already do some research. So let's write a diffusion. So this is called diffusion process. So this is a function called dxt. So dt plus diffusion. So txt dbt. So this is a general form of SD. Right? It's a general form of stochastic differential equation. So this is a general form of stochastic equation. Okay, so usually, so I mean, you probably don't know the meaning, right? So usually, what does this mean? Of what if we say this is SDE, right? So if you learn a little bit about ordinary differential equation, we know, right? So this basically means, right, xt solves continue the integral equation, right? Not a differentiation equation, right? So bs xs ds plus integral from 0 to t theta s x s dbs, right? So basically means the following integral equation. I mean, of course, right, this is a Euler-Riemann integral, but we don't know, right? So what's this? Right? So we don't know what's this, right? So this is the Ito integral. We will specify in next lecture when we prove Ito's formula. But what I want to say here, right, is a form. We'll say the following. So if this term equals to 0, this term equals to 0, so then xt is a martingale. Then this is a martingale. Right, then this is a martingale. Okay. Any questions? Okay, you don't have questions. Yeah, maybe we start a little bit, just write a little bit more. So these two lectures is just a beginning, right, of a totally different course, right? So it's It's usually we call this stochastic analysis. Yeah, this is a quite a big field, right? So there are many people working on that, right? So since nowadays people are very interested in right. I mean, this is an old field, right? This is a very old field, right? I mean, so many people are working on that, right? So the many, right? Thinking. So the many people study this, right? So probably, right, in probability community, there are many people, and also in dynamical system. So if you study the behavior dynamical system, they use stochastic analysis as well. And also, right, of course, right, people doing PDE, right? And nowadays, right, people is doing data science, right? Machine learning, they need use this, right? So why, right? So I can tell you, right? Right, for a very easy example. So for instance, let's say if you want to find a minimum of a function, right? Of a function. So usually, do right, is doing something like gradient, right, of st. Right? It's the gradient descent. Right? But sometimes you cannot do that, right? So you just do sampling, right? Not do sampling, right? So probably you do this, right? The gradient you probably involving many terms, right? So sometimes you do like stochastic gradient. But this probably not really relevant, right? It just has stochasticity there, but not in the explicit form. But you probably know, right? It's called Lorentz dynamics. This is the easiest stochastic differential equation, right? So like this, right? dxt equals minus xt dt, right? This is the diffusion, the how to say that, friction is basically friction, and you plus dbt, right, Brownian motion theta, right, is coefficient. So this is called longitudinal dynamics. In general, you can put a more general form, right, minus gradient phi xt, a potential function xt. Right, so this is first used to study gas dynamics. So this is called longitudinal dynamics. I believe, right, when Einstein first derived Brownian motion, he used this. He basically used. So people use this to study fluctuation, dissipation. So this is used a lot in physics. It's kind of some zero limit of some second order system, right? If the Newton dynamics, if the mass is very small, right, you have in the very small mass limit, you get this equation. Right? This is one example, and this is used a lot. This is used a lot. For instance, you use this of like a Fokker-Planck equation. So Fokker-Planck equation, right, is like ut gradient phi, right, plus sigma square gradient 2. Right? This is actually, right, so you using longitudinal dynamics, right, or MCMC, right, to simulate, right, so some PDE, right, to solve maybe not a PDE, but physical system, right, essentially, right, quantum or even. Yeah, this is a very important field, right? So if other faculties and Penn will be willing to teach something about that, right? It's very useful field, right? So even if you are doing data science, because in the end, right, since you have a lot of data, so you need some continuous tools, right? because it's high dimension, right? A lot of data, right? So people believe they need to use some continuous type of, right? So stochastic analysis relation to PDE is actually really useful, right? So that's why, right? So the ETOS formula is one of the basic tools there. I will stop. Basically, I will stop. If you have things, you can just leave the meeting. Next lecture, right? In next lecture, we talk about the ETOF equation, right? So basically, what does it mean, right? So what's the meaning of this? Of course, you know the meaning of this part, right? I want to say, right? What's the meaning of this? Right? So we want to define, right? What's the meaning of the ETO calculus? So what does this mean, right? But we cannot do like too deep, right? Too deep way. But I will show you. There's three formulas, right? There's three formulas in the textbook. Basically, that's good enough, right? That's already captures a lot of things. But there's no discussion on SDE, but they already discussed a lot of things. But everything regarding on EF, right? Regarding on this, right? There's several formulas, right? So as I said, right, first one is DFT. So if you have this, right, there's no time dependence, right? So there's only X dependence, right? So we just use this, right? So Euro calculus, we are stopped here, right? But it's not the Euro calculus, right? We have stochastic term, right? It's point motion. So we take a second order derivative, right? So then we have one more terms, right? It's the Taylor expansion up to second order term. And we will show, right, why I say this equals to dt, right? So yeah, why we say this is dt, right? Basically, by in your previous homework, right? So this is basically ti minus bti minus 1, and you sum up the partition pi, right? So pi is a partition. So then you have convergence to t. So pi is a partition from 0 to t, right? So this t1, t2, right? So this is tn. If you let the partition to be as small as possible, so this can be almost surely. But of course, this is in L2, right? You put this in L2 and also in probability and also almost surely, right? So we have this convergence, right? So this basically tells us, right, dbt square, right? So is dt, right? This is just formal writing. First one, right? And there are also others, right? So f depends on time as well. What is the differentiation? Right? If f depends on time, right? So then, right, there's one more term, right? There's one more term. We take derivative in f, right? And also we take second order derivative in x, right? So then this is dt. And there's also partial xf terms, right? So this is dbt. So this term is a martingale term, right? This term will give you martingale, right? So that's why if you have this equal to 0, you get martingales, right? This is the second form. Another, right, is multi-dimensional version, Okay, but that's not all, right? So if we have xt, right, which solves SDE, so let's say it solves dtxt dt plus sigma txt dbt, right? So then what is the formula of dftxt, right? So then what's this formula? So there's no discussion about this, but this possible is the same. So it's txt, and now it's t, right? So then you take the first order derivative of x. So then, right, this is dxt term, right? So then the second order derivative, partial square, dxt square. So, but in the end, we should expand this term, right? So what is dxt square, right? So we take everything, right? So this is bt xt dt plus sigma tt dbt square. So then we just complete the square, right? So this dt square vanish, right? dt, the cross term dt dbt square vanish. So in the end, we just get this dbt square, right? As I said, right? So this equals to dt, right? So this is more general, right? Yeah, we just basically tell meaning of all this for next lecture. But definitely we don't have enough time, right? So so for more discussion on SDE, right, you probably can find a book. Yeah, yeah, I will tell you next time. Yeah. Okay, yeah. So you can leave the meeting you want, but I will ask you questions. Yes, yeah. The next lecture is the last one. Yeah, yeah. Okay. Yeah, thanks. If you have questions, I can answer, but otherwise, you can leave the meeting.